back again. Got another StatMech video for today. What I think I'm going to try and do now, and this is kind of as a study tool for myself really, is I'm going to try and go over the topics that I go over in lecture, and I'm going to get the material from the textbook we're using and try and supplement it to you, because if I feel like if I can teach this material to you guys, once again, maybe I myself can have a better understanding of how or where these formulas come from, how they work, so on and so forth. So, in this particular portion of today's upload, we're going to be emphasizing section 5.1 of Reif, and we're going to be going over the equation of state and of internal energy of some sort of ideal gas. Now, typically, if you remember from like down to grade school, right, when you're learning about thermodynamics, we usually treat an ideal gas as having the properties dependent on this particular formula. PV equals nu RT, where P is the pressure, V is the volume, nu is the number of moles of our substance, R is an ideal gas constant, and T is our absolute temperature in degrees Kelvin, right? Now, all this particularly does is that it macroscopically characterizes our system in a way that it can just summarize the general phenomena of some sort of experiment that we do. So if we do some sort of experiment with gas and we assume that it's ideal for that particular case, even though it probably isn't, we can make estimations of what will happen to that particular ensemble of gases, or just that ensemble of gas with this formula here. It's just a good meter stick, basically. Now, we've typically only ever noted that an ideal gas's energy is dependent on the internal temperature, right? So if you want to change the internal temperature of an ideal gas, all you do is you just crank up the temperature, you increase kinetic energy, and you've got more energy in your ensemble, right? However, whenever we're dealing with real gases, this doesn't always necessarily hold. So what you end up getting is this definition of energy that is dependent both on the temperature and the volume, right? Because if you think about it, as you increase the volume of a gas, you might not think that your kinetic energy will increase with it. You might think it might decrease. If you, if you take, for instance, a bunch of gas and you compress it down, there's less space for those particles to move in, and they're more cramped, they're denser, they bump around a lot more, there's more vibration, you'll have more kinetic energy, right? So for real gases, we'd assume, well, yeah, energy has to be dependent both on temperature and volume too, right? All this does is that it allows us to effectively define our differential of energy in terms of partial differentials, right? So our differential of E can be expressed as the partial derivative of E with respect to temperature, holding volume constant times some change in absolute temperature, plus the partial derivative of our volume with temperature constant with respect to a small change in volume. Now typically I might go on down later in the proof itself on the right hand side, and I might drop what it's constant with respect to, but because this is a multivariable function specifically with only two, just assume that it's constant in the other one unless otherwise indicated, right? So if we know what our energy is, what we can do is that we can go back to our fundamental thermal relation for some quasi-static continuous process, right? Because we're dealing with small incremental changes of our variables. So we're going to start out with the quasi-static case, obviously. And that relation is that our temperature times some small change in entropy is equal to our inexact differential of heat, which is just equal to our change in energy plus our change in work, which we can express as P dV. I wrote it backwards because I was putting the cart before the horse like I normally do. If we divide both sides by T to get the change in entropy by ourselves, and then do some algebraic manipulation, we can re-express our change in entropy in terms of the partial derivatives of our energy, right? So with that in mind, we can also draw a parallel, a very nice parallel here between our differential definition of ds and what we have here explicitly written out in terms of temperature, energy, volume, moles of gases, and the ideal gas constant, right? So before I jump too far ahead in the proof, I'm going to talk about what I did, right? We divide both sides by t, and then we know that dE over t can be rewritten as 1 over t times the partial derivative of E with respect to t holding volume constant. And the same thing over here with mu r over our volume v dV. You can re-express that this way as well. I showed off to the side here in blue how we can do the substitution for this term here specifically. What we do is we just take our ideal gas law, reorganize it in terms of P or our pressure, and then we just substitute it. In Kablamo, we've got that over there, right? So with that in mind and those substitutions in mind, what we can do is that we can compare what we have explicitly derived for entropy and what we can get from just the general definition of our differential ds. So with that in mind, we can say that our partial derivative of our entropy with respect to t is equal to the 1 over t times partial of E with respect to t, and our partial of S with respect to volume is that smaller other sum where we have a partial differential of E with respect to V plus our ideal gas constant times the number of moles divided by the volume of our gas. Now we can actually begin playing around with some of our properties of our differentials. We know that something can represent a valid differential equation or valid double partial derivative if, I believe it's actually the definition of an exact differential, if we know that our second derivative of our object in interest, this time being our entropy S, can be derivated partially with respect to its two variables in either order. I believe this would generate ourselves an exact differential. So what we do is that we apply this rule to our entropy. So we can imply that our change in volume, derivating our change in temperature with respect to entropy, or entropy with respect to temperature, is the same as if we did the partial derivative of temperature of the partial derivative of our entropy with respect to our volume. That's all that really says. It's more of a mathematical statement. And what we do is that we extend this idea over to our partial derivative with respect to energy, right? So we have our differential of energy, or we take our energy rather, and we derivate it twice, first with respect to volume, and second with respect to temperature, and then we just essentially just drag and drop what our partial derivative terms are in both cases, and then we set that equal to one another. And whenever we do our little cancellation of terms here, what we learn is that since these guys are equal to one another, they cancel out, leaving this whole term here set equal to 0, and because this whole thing is equal to 0, then we can actually note that our partial derivative of energy over our volume with respect to a constant temperature is equal to 0. And if we have any sort of partial derivative in which our result is equal to 0, then we know that our energy has to be some sort of constant. So we can basically conclude that our energy is independent of volume, or rather that volume is constant for this particular energy. What this really shows is that we can actually find an ideal gas, or assume an ideal gas, which is what we do up in our ds statement at the top of the right-hand side, and then show from that that for that ideal gas, its energy is only dependent on temperature, or rather a change in temperature.